Welcome to the Network Plus video training course. My name is Paul Browning. I'll be coaching you through the network syllabus from beginning to end. For the past couple of iterations we just added updates to the end. So for the 005 we added some 006 updates from the 6 to the 7, so you'd go all the way through the syllabus because there wasn't that many changes. We decided for the 008 to start from the beginning again because it's time for a complete fresh update. There'll be theory, and also at the end of the course there'll be some labs. Now the labs don't depend that you've read the theory or watched the videos, so if you want to dip into those at any time if you don't feel like going through the theory, or if you want to go all the way through the course and then have some fun with the labs. The labs aren't compulsory because there's no hands-on labs in the exam, but they really do help you understand the concepts far better than just listening to me explain them. So I recommend you do go through them at least once. So Module 1, Lesson 1, we're going to talk about the OSI model. This is the Open Systems Interconnect model, and it's covered in many different vendor exams, including Cisco, and it's a way for us to understand how internetworking works. So we'll look at the OSI model. We'll also look at some encapsulation and de-encapsulation within the context of the OSI model. So this is what it looks like in full. The first thing to emphasize is this is a model. It's a way of us understanding what goes on in the world of networking. So you won't actually see this spelled out anywhere. The closest time you would actually see it, if I can just get my pen tablet, sorry, I swapped between the clicker and the pen. The closest you'll see probably when you're thinking about the OSI model is if you capture a packet. Now if you're wondering what this is, it's supposed to be a magnifying glass, sorry. You'll capture a packet, and if you use Wireshark, which I highly recommend you learn, we've got a course on that on how to network. It really helps you do a deep dive into all of these layers, and it will actually separate the packets that you capture on the wire into these layers. But generally speaking, as network engineers, we don't see these anywhere. It's just for us to understand a way of making sense. You'll notice that there's 7 layers, and we always start off at number 7 on the top. 6, 5, 4, 3, 2. I always have problems with 2s with this pen, I don't know why. And then a number 1. Oh, there we go. Vanished altogether. So, try again. I mention this because when you're working on a network, say you're a network engineer, you'll be speaking with another engineer, and they will say something like, oh, I've got a problem, or you're looking at a help desk ticket, and they'll say something like, oh, I think that's a layer 3 problem. Now if you don't know that layer 3 corresponds to the network layer, it's just going to be a bit embarrassing. Or they could say, oh, I recommend you check the check layer 1. Now this is just how network engineers speak, and even programmers and other network people. So what you'll need to do is know that they're talking about the physical layer, the session layer, or whatever. So this always starts off at 7. Number 7 is always the application layer. No one will ever do this. That doesn't happen. So if you ever see that in a book, it's wrong. The other thing is you can see each layer, 7, 6, 5, 4, 3, 2, 1, has a name, and you'll need to know. So in the exam they'll say which layer is number 4, for example, and you'll need to know that it's a transport layer. So how do you remember all of these names? The easiest way is with mnemonics. So you take the first letter of each layer and you'll create your own mnemonic. So the one for OSI that seems to work for people is all people seem to need data processing. So if you say to yourself, all people seem to need data processing, that's probably the most common one for the OSI. Now for other parts of the exam, yeah, definitely make your own mnemonics up, but this is the common one used for the OSI model. So these are I'm trying to sort of help you become a good network engineer and also get you through the exam, because you just kind of have to remember things like this. So I'm going to go into the explanations now, but I just wanted to go through that before we actually start. So what is it? What is the OSI model? It's a way to describe a network and systems functions and to characterize the various tasks that each one carries out. This will actually become clearer as we go, but for now, just imagine a conversation between two people. Now, to ensure effective communication, the first thing is we both need to be speaking the same language. So rather than both trying to speak at the same time, we take turns. That's the second part. So if we're having a conversation and something is misunderstood, you can ask them to repeat it or confirm you understand what they've said. You can also ask somebody to slow down if they speak too quickly. All of this can actually take place at the OSI layer as well. All of these requests can be done, but it's done in a formal manner. Now, generally speaking, as consumers, we don't have to worry about any of this. We'll send an email and it will get there, or you could receive an undeliverable message into your inbox. As a network engineer, we do have to be concerned about this kind of thing though. Now, one advantage of the OSI model is it gives vendors of different equipment a way where we can have our products interoperate with one another. So for example, you could buy, I'll cover this later, but you could buy switches which are working at the data link layer from Hewlett Packard. You could buy your routers. I'll say Cisco because I'm most familiar with Cisco, but as you know, there's a load. So you've got vendor 1 here and vendor 2 here, or you could have a Cisco router speaking to a Hewlett Packard router. Now, if these devices all agree on the same method of communication, then everything is going to be fine. It used to be many years ago, if you bought a vendor's equipment here, it would speak language X. For example, I'll put 80 for Apple Talk, and over here it would be using the OSI. So these two methods wouldn't work because they're speaking different languages or protocols. So if we follow the OSI model's rules, it ensures that all entities are compatible with each other. This allows all vendors and developers to recognize how data is transmitted over networks, including the internet and even mobile device networks. So the OSI model can help new technologies adapt and grow. It also shows how software and hardware interacts together. The reason is it can identify the most likely cause faster than guessing and using a process of elimination. So often as a network engineer, you'll have somebody report a problem for you, and with a bit of experience you'll have a good idea. If somebody says packets are dropping or whatever, you could think, oh hang on, it could be a physical layer problem, and you could check the cable. We'll go into this later. And then if everything's working with a physical layer, you could then work to the next layer, check the data link, next layer, and work your way up. So this is bottom up. Other network engineers, or depending on who reports a problem and what they tell you, you could work from top down. So you could think, okay, well, let's look at the application and then work your way down the OSI model. Again, you can't see this. This isn't something that you would open up a computer and see any of these layers here. It's just a way for you to conceptualize. So we can see the stack's divided into 7 layers, and each has a specific role ensuring mutual communication. Now you'll need to know generally what each layer does and what it's responsible for. So if we start at the physical layer, this layer primarily is in charge of sending digital data bits from a source device to a destination device. This is over a physical network. Obviously now we've got wireless networks, so it could be a communications medium, we'll say. So we've got several hardware components required. We've got the cables, connector types that go at the end of the cables, network interface cards, repeaters. The repeater generally amplifies the signal. So if you've got a wire here and a signal going on a wire, it can start off quite a powerful signal, but over time actually lose its strength. So a repeater is a device that can actually boost the signal here, so it's full strength again. It doesn't contain any programming, so nobody's doing any coding. It's literally sending bits over a wire, or it could be wirelessly. Because we use a wire here in this example, it can only send data in a electronic format. So a pulse is on the wire, which is an electronic pulse, and it's not on the wire. On the wire, it's not on the wire. If there's a pulse on the wire, it represents a 1, and if there's no pulse on the wire, then it is a 0. I've put these separated, so 1 0 1 0, but it could obviously be 0 0s and 1s and 1s, but just to make it easier to see, 1s and 0s. So this is why we use binary communication, and this is how the numbering system works. So this would include for wireless and physical mediums. For wireless, that information must be converted into electromagnetic waves. Obviously on a cable it's an electronic pulse. So to imagine the transmission, we see data link information becoming on the system it's about to transmit. It then gets converted into 1s and 0s from the DLL. This is the dynamic link library. I'll check the syllabus to see if they mention DLLs. You've got to be careful because CompTIA say we can ask stuff that isn't mentioned in the syllabus. So check the end of the syllabus where it's got a glossary of other terms that you will see mentioned, but it might not be in the syllabus. So have a look for the dynamic link library. So this converts the physical layer into electrical impulses that can travel across the cable. So you can consider all these to be 1s and 0s as a pulse. So these 1s and 0s go over the wire, and all things being equal, and say there's no fault in the wire like a break or it's fraying or somebody's bent the interface back in some way, all of these 1s and 0s should match when it gets to the other side. Now we'll go through error checking later, but if it matches, then it would have passed the error checking process, and then it would be sent up to the next layer of the OSI. Alright, so that's the physical layer. Bear in mind the notes here of what this, if each layer's got a job description, you'll need to know it for the exam. So the job description for the data link layer, data delivery from node to node. There's other things that happen at this layer which I'll come into in a moment. For example, this is a physical address. Physical addresses can also be called a burned in address. Just depends which vendor you're studying with, and I know that obviously CompTIA's vendor neutral, so this is why you need to know maybe a couple of different terms: physical address, burned in address. So as data comes down from the network layer on the sending side, we start to see more layer-to-layer communications. So then the data link layer can go down to the physical layer, or it can go up to the network layer, which is the next one. So we have physical addresses. This relates to node-to-node communication. So you can actually communicate between two devices just using the physical address at the data link layer. So this will be intended for a specific network device. Now we'll contrast this in a moment with the physical layer, which has, we've already seen the physical layer. This has got no physical addressing. So if you've got a just your network cable here, you'll notice that there's no way of knowing who's at this end and who's at this end. There's no addressing. The actual data link hardware addressing, burned in addressing, takes place, sorry about this pen tablet, at the data link layer. This is responsible for the physical addressing. So the data link layer, this defines the correct structure for the network type being used. It also implements access control, which I mention just here. So flow control can help manage the data transmission and reception. Error control helps improve the data transmission reliability. So we see much more data processing here than at the physical layer. Data link layer is also divided into two sub-layers. This is actually covered in the Cisco CCNA. So the data link layer, you'll see in some diagrams, has a split in the middle, and the top layer is the LLC, logical link control, and then the MAC sublayer down here. So this communicates with this layer, and again this is a concept. You won't see this if you plug in or look at the actual device. So this is again a way of just making more sense of what's happening at this layer. So for functionality, the LLC, logical link control sublayer, determines whether communication is connectionless or not. So you can imagine connectionless as a speaker. The speaker isn't addressing anyone in particular, so you as a person in the audience can either listen to it or ignore it. Now you can imagine connection oriented as a two-way person-to-person conversation. So one person speaks directly to the other, and that's how that would work. This concept will come up again when we discuss the transport layer, but it's not uncommon for the layers to share some functionality. This is what makes the OSI a little bit difficult when we come to answer exam questions. So based on the LLC definition, high-level protocols can be used. The MAC sublayer is found at the data link layer's lower section of the two sections. So this layer is also acceptable in everyday conversation. This may be the most critical section of the OSI model. This is where the MAC address or the physical address or burned-in address, depending on which book you read, is processed. The MAC address is a 12-character hexadecimal value that is unique to every network interface. We'll go into looking at the addresses later on, and we might do a lab on this. So for example, a standard network interface card in a computer stores this value directly. Say you take a network interface card out of a computer and put it into another one, the MAC address on that card will stay the same. It's physically burned into the chip, and it's also the same for ports on devices such as routers or switches. It always stays the same. So ultimately this value allows any node to locate any other node and initiate communication. Now direct node-to-node communication is impossible without this physical address. Alright, so now onto the network layer. So this is our layer 3, third layer. So the name network obviously gives us a big clue as to what's going on. It's a bit of a generalization in terms, but and a broad term, but it's basically what's required to communicate between devices, and it all happens at this level. So the network layer will receive data from the transport layer as it travels down the stack on the transmitting side. It will then process it and pass it down to the data link layer. Now in terms of specific functionality, this layer handles things like packet addressing and address conversion. It's worth noting, again for exam terms, this layer here can only communicate between the next one up and the next one down. So what you won't have in the OSI model is the network layer skipping and going all the way up to the application layer, for example. That's not permitted in the way the concept works. You'll also see here that the addresses that we're discussing, so here we have the physical address, we'll call it the MAC address. The network layer is concerned with the logical addressing, which I'll cover in a moment. So this is the familiar addresses that you could have seen before at home or at work, your 192.168.100.1 and other similar looking addresses. So I've mentioned this is a logical address. The data link addresses are physical addresses, burned in addresses that stay the same. You can actually, it's outside the boundaries of the syllabus, I think, but you can actually go in if you're on a Cisco device and change the physical address, but we won't recommend that for the purposes of the Network Plus. So the conversion here is from the physical to a logical address going down the OSI. To give you a better idea, if you switch to mobile phone providers, you'll be given a new phone number, but it's actually the same phone. So this is what can happen with the network layer. You can have the same device, but it can have a different logical address. So the same is true with computers. Now, like in the data link layer, an IP address can provide source to destination delivery. This happens at the network layer. This layer also introduces you to routing at the network layer, allowing source and destination networks to be partially separated up to and including the internet. No device or service can use physical addresses to route. So just this is another exam question. Your burned in address, your physical address, MAC address, this won't go out to the internet. So if you're ever talking about internet communications, devices of the internet communicate using these addresses here. So I'll just do ticks. Alright, so now we're onto the transport layer of the OSI. This layer here accepts services from the session layer above and passes them to the network layer before. So we've already discussed this. When say you're over here on device A and device B is over here, so you'll compose your email and each layer will do a different role, whatever the role is, as we're discussing as we go along, and it will pass it down. You'll send your email, it goes all the way to the other device and it goes in the opposite direction. The wires, the signal on the wire to the data link layer to the network, and so on. Now you don't have to use all 7 layers. This is a mistake people often don't realise. For example, if you're pinging a device to another device, then you'll stay at the relevant layer for the ping packet. If you're emailing another device, it will go all the way up. If you're doing a test on the cable, then you may only use the first 2 layers on either side. So the transport layer is primarily concerned with message delivery and error checking. And again, we're concerned with ticking the right boxes in the exam, so make sure you're familiar with the two main roles here of the transport layer. So to clarify, the end-to-end component ensures that one system can locate another using a logical IP address at the network layer and a physical or MAC address at the data link. This isn't all though. Both types of addresses are device specific. Now, given any device can have multiple applications and processes running to communicate, you must first locate the device. So to which device application is the data being sent? On a computer, for example, you can use a browser and a local email application at the same time. So if you load a web page while an email arrives, both applications' packets arrive at the same address. So how does the browser know which packets belong to the page? Who knows which packets contain the email content? Well, this is where your end-to-end communication comes in. So not only the address, the primary protocols at this level define values to distinguish between application protocols. What we'll use in TCP/IP networking is a concept known as ports. You may have heard port numbers even if you're new to networking in relation to particular types of traffic. So the transport layer will add a port to the packet definition to let each system know that the packet is not only for a certain address. Common question also for transport layer is error checking. So the job is that the packets arrive without duplication or corruption and in the correct order. So packet 1, 2, 3 is sent. If it gets arrived as 1, 3, and 2, then it will know what to do to reassemble them in the correct order. So it's also intended for a specific application at the address, talking about port numbers. Error checking is implemented at the transport layer. We need to keep in mind that each systems layer only communicates with its counterpart, as I mentioned a moment ago. So this layer's error checking ensures that packets arrive without duplication, corruption, correct order, and it's more specific to the service or application being used, and which is it's unaware of the lower layers. The transport layer also handles message acknowledgement and traffic control. Now this actually depends on the protocols being used, and it can vary from protocol to protocol. The ability to combine multiple message streams or sessions into one logical link while keeping track of which message streams belong to which sessions is the job of the transport layer. Now, service point addressing, which specifies applies to the port value, which I mentioned briefly. Now, when it comes to data delivery or transport, there are two main protocols. I'm sure you've heard of these if you've been in networking any number of days or even hours. We've got UDP and TCP. UDP over here, have I spelled it out now? User Datagram Protocol is UDP. It's all very complicated. You can tell engineers put this together. Transmission, control. I say this because everyone says TCP, UDP, however you'll need to know which is which for the exam. As a general rule, for UDP package delivery, it's for a service where you don't care how it gets to you or even if it arrives. It doesn't do any check-in. TCP is a reliable form of communication. We'll be going into this in more detail later on. Alright, so this is layer 5, or for short, or we can call it the session layer. So the session layer's job is managing communication between two devices, including at the start of the session, its continuation communications, and also how the session ends. So we need a way to agree how to say hello, have the dialogue, and then end the conversation. So overall, it's controlling the data flow between the devices. So we've got a few important roles here. Start, continuation, and then finally the end. Session protocols are also responsible for defining the connection parameters. They manage the data transfer by defining who can transfer and how long. So this is the rules of the conversation before the conversation actually takes place. You can consider the session layer as a debate moderator to make sure everyone gets a turn. So we'll examine the session layer's functionality in relation to what's actually happening. When we establish, maintain and terminate a session, clearly this is what allows the two systems to establish the session. It's rarely as simple as let's talk without any other considerations. One of the most common session support requirements is security. So using name recognition or more commonly a login. It's not always necessary to log in to use a secure connection now. So when they are logged in, the session layer must negotiate to ensure all security concerns are met. The session layer also manages dialogue control. This is which device communicates first, who can send data from each device, and when. Dialogue control comes in three flavors: simplex, half duplex, and full duplex. Simplex means you've got a one-way communication, so that is one device transmits while the other listens. A practical example would be like walkie-talkies. If you ever had one of these, or if you're getting old, you'll know that one person presses the little button on the side. When that button's pressed, the other person can't communicate. So the signal goes that way. When they're finished, this is why if you've ever had strict communication, somebody will say over, and that means the other person can press their button and then send their message. Half duplex means traffic can go both ways at the same time. Each party must take a turn. So think of it as a phone call. To transmit, we don't need to press a button. And now we can all speak at once, of course, but that would make the conversation difficult to follow, so we alternate for clarity. Full duplex means traffic can be sent both ways simultaneously, so both parties could speak simultaneously and be understood. So if you imagine a conversation, we don't normally speak like this, but computers can do that just fine. So nowadays, most communication is taken care of by way of full duplex. I won't go into details here, but wires on if you've got a cable on your network, wires are allocated to send and there's wires allocated to receive. Beforehand, for half duplex, that wire could send, it would have to wait, and then the same wire would wait until there's a clear signal and then take its turn to send. This is why we can have two-way communication with full duplex, and most devices are doing this now. Some older devices or applications may not support full duplex. Some session layers such as NetBIOS and DNS, domain name system, Now both methods of communication involve name recognition and resolution. Requests are generated on clients but executed on servers using RPC, that's short for Remote Procedure Call. So there's also NFS, which lets clients access server-side resources like folders and files. And then finally, the session layer is in charge of negotiating and maintaining the session's flow. So you can think of this as the moderator for a conversation. Alright, so now we're up to the presentation layer. Now the clue is in the name. The job of the presentation layer is to present data. It says represent here. You could also just call it present data. It does this in a uniform format to the application. So in other words, it hides any data differences between the two systems. The presentation layer is also sometimes referred to as the translation layer. I say sometimes, it's pretty rare, but it's something you just need to know. So we'll get to that in a minute. In terms of imagining what happens at the presentation layer, it's better to imagine the information going up the stack. In most of my previous presentations, I talked about how data moves down the stack onto the sender. But of course, it goes up to the receiving stack, which I mentioned earlier. We can then look at the presentation layer. So the whole point is to present data to the application in a format that the application can understand. So why doesn't the app get it? So we're back to the translation. It converts data into a format that the receiving application understands. Refreshing the stack data is now being sent, but the sending and receiving systems may not be fully compatible. The reason this would happen is they're running different operating systems or apps. So sometimes you could have a device sending something in a JPEG format and the other side is trying to read it as a GIF. That's just a generic example. So the data may simply have arrived in a format that the receiving application doesn't understand. The presentation layer must examine the data to decide how to make it understandable to the application. So define possibly incompatible now. Let's look at some of the functionality here. So this layer's responsibilities include character code translation. Don't think I wrote that down in the notes there. So we as humans use what is considered standard characters. In the end, all digital devices use ones and zeros, so we need a way to turn those characters into the ones and zeros into characters. The two most common formats are ASCII, which is the American Standard Code for Information Exchange, or XML. XML is Extensible Markup Language. I'm not sure if they'd want you to know that in the exam, but you can check the glossary at the end of the syllabus. Alright, and we're at the application layer. So this is where we'll spend most of our time as people who surf the web, or if you're working in an office. Most people won't be concerned about anything that happens after they click send on an email or if they click on a web page. So as users, we might think of the application layer as a software interface we use. This is how we communicate with the device. Now, in the OSI model, in terms of us as network engineers, we need to think of a collection of protocols that support the application's functionality. So let's send an email, for example. Many email clients can do more than just send and receive emails. You might make a note, add a contact, schedule an appointment. But if none of your tasks necessitates your system to talk to another, they're just app features. So we use the interface again, but nothing happens in terms of connectivity. In order to send an email to another person, we need to start thinking in terms of communication protocols. One example is SMTP, or Simple Mail Transfer Protocol. This is a common messaging protocol. The application needs that protocol to do its job. Other examples is our favorite, which is using a browser. Now, if this is all new to you, you may have missed it, but in the browser's address bar, you'll often see HTTP, which stands for Hypertext Transfer Protocol. So this is the standard internet data transport mechanism. So the browser application tells the other system what protocol to use to send the data. And we have many application protocols at layer 7. There's a number mentioned in the syllabus, which we'll go through later on. Some examples are FTP, which is used to transfer files, normally larger files. So this reliably, if it's a large file, as you can imagine, that would use TCP to send the file to the other device. DNS is a domain name system. I mentioned SMTP. HTTP is our favorite. It's used for internet pages. DHCP assigns IP addresses to client systems, and we resolve names by DNS. So for example, if you typed in howtonetwork.com into your browser, somewhere along the line DNS would need to pull up the IP address. I'm just going to make a random one up, 70.1.1.1, so the traffic can actually be sent across the internet. As long as the appropriate application layer protocol is used, the developer controls the application's functionality. So somebody could do all the coding they want as long as they comport with all of the particular rules of the protocol.